Hello and welcome to the session of cable modeling with CGAP element in Hypermesh OptiStruct user profile. So in this session we will see what is CGAP element, then PGAP property, and then finally an example on CGAP element in Hypermesh. So let us see the CGAP element. So CGAP element defines a gap element or the friction element, and for the linear subcase, the CGAP element will produce a linear stiffness matrix which which remains linear with initial stiffness. So the x-axis point in general direction from body point A. So as we can see here in the schematic diagram, so the x direction, the body point A, that is the grid point A to the grid point B, it acts to prevent contact or overlapping of those bodies, and the stiffness depends on the value of initial gap opening. Now let us see CGAP card parameters. So we have EID, that is unique element identification number, then PID, that is PGAP entry property identification number, then GA and GB are the connected grid points at A and B. Then we have XI, that is component of the vector orientation vector from GA in the displacement coordinate system at G. In we have G theta, that is alternate method to supply orientation vector using the grid point G0. Then we have CID, that is element coordinate system identification number. Now let us see PGAP property. So it defines property for gap elements, that is CGAP or CGAP G elements. So in the PGAP card, we have PID, that is property identification number, then U theta, that is initial gap opening, F theta is the preload, K is axial stiffness for closed gap, positive value prescribes the stiffness, and the negative value prescribes stiffness scaling factor. Then we have KB, that is axial stiffness for open gap. KT is defined as transverse stiffness when the gap is closed, and mu1 and mu2 are the coefficient of static and kinetic friction respectively. Now let us see an example on CGAP element. For that, opening Hypermesh. So this is the model we are going to consider for this tutorial or this station. So this model is meshed with a 2D element. So now let us review whether the components are defined with material and property or not. So the components are assigned with material and property. Also, this model has a predefined load collectors, that is NL param, which is used to activate a nonlinear solution method. Then we have NL adapt, it is used for adaptive control card, and then we have NL out, which is used for creating intermediate output requests. Then we have material, name as steel, and card image as mat1. Here is the Young's modulus, Poisson's ratio, and mass density. Then the property, we card image as P shell for the 2D elements and the thickness of 3 mm. Now to create a PGAP element, CGAP element property, right click on the model browser, click on create, and then go for property, name the property as PGAP. Under the card image, search for PGAP. So U0 is the initial gap opening, F0 is the preload, leave it as the default value. So K is axial stiffness for closed gap. So check it for the real value and define K as 50,000. Define KB as 0 and leave the other field as by default. Now to create a CGAP element, first we have to create one component for that. So creating a CGAP component. Now under the 1D option, go to the gaps, select element type as CGAP, define property PGAP, and select the nodes that is point A and this is point B. So this will create a CGAP element. Similarly, then click on return. Now to assign the coordinate system to those two elements, go to the card editing, select an element, click on edit. Under the CID option, select user, and in the CID select ID as 1, that is local coordinate system, which is predefined in the system. Then click on return. Similarly, select other element, repeat the same process. Then click on return. So while defining the coordinate system to this elements, this will show you the direction from the direction grid point A to grid point B. So it will act to prevent the overlapping or the contact between those two bodies or those 2 points. Now to create constraints and loads, we have to create a load collectors. So for creating load collectors, right click on the model browser, click on create, and then load collector. First we have to create constraints. So for creating constraint, click on analysis panel and then click on constraints. Select the nodes, select load type as SPC, check on all 6 degrees of freedom, and then click on OK. So this will create constraints in all 6 directions. Now to create a load on those body, create a new load collector name as tension. Go to analysis panel, click on force, select the direction as x-axis, define the magnitude as 100, select load type as force, select the nodes on the model, click on create. This will create a tensile force for this face. Similarly, create a tensile force for this face. Define magnitude as minus 100 and then select nodes and click on create. This will create a tensile force for this model. Now create another load collector for compressive force. So the current load collector is compression. Hide the force for tension. Now select the nodes on this face to create a compression force. So the value is minus 100. So this will create a compressive force on this face. Now to create a compressive force on other face, this will complete the compressive force on this face. Now to create a load step for tension, right click on the model browser, click on create, and then go for the load step. Name the load step as tension. In the analysis type, select nonlinear static analysis, define the SPC. Under the load, define the tensile force, define the NL param card. Similarly, define NL adapt and NL out card. Now create a load step for compressive force. So in analysis type, change it to nonlinear static analysis, defining the constraints. Under the load, defining the compression force, defining NL param card, NL adapt and NL out card. Now to create output request, go to analysis panel, then click on control cards, search for global output request, search for displacement, set the format as H3D. Now search for EL force, this is the elemental force, define format as H3D. Now search for stresses, and define the format as H3D. Then click on return. So this load step is for the tension, and then this load step is for the compression forces. So in the CGAP element we have a CID option. Let us check that other CID option. So if you click on the elements and click on edit, so we have CID option as the flip. So this will what it will do is it will reverse the orientation of the x-axis of the gap coordinate system. So this will the CGAP element will behave exactly opposite to what we have defined in the previous way, that is we have to define the local coordinate system for that. So we will discuss this in the hyperview later. So now define the param card. For defining param card, go to control cards, search for param card, define the check element as no, so the OptiStruct solver will not check for the element quality. Then click on return. Now search for screen and set the value as out. So it is used for echoing out the .out file while solving this model. Now export this file and save this file in your desired location and solve this using OptiStruct. So I have already solved this model, and I load the results in hyperview. So opening hyperview, so this is for CID as a user. So when we define the CID as user, so it will prevent overlapping of both the body, that is grid point A and grid point B. So as we can see, there is a deformation in tensile load case. So we have tensile load case deformation as 39.89. so if you calculate the relative displacement between that, so it will be around 79.79. so the total distance is now 579.79. and similarly for this compressive load case, if you measure the distance between, so the distance between is approximately 500, so there is no change in the compressive force. So this means it is acts to prevent the overlapping or contacting the body A and body B. Now if you select the CID option as a flip, so this will result in the zero displacement in the tensile force load case, and there is one displacement of it around approximately 79 mm, approximately 80 mm of displacement in compressive. So this will behave exactly opposite to what we expect in the CID user option. So it will not prevent the overlapping of the body A and body B. Also, if you want to check the elemental forces acts in the CGAP element, so click on the contours, change the result type to EL forces and select the element and click on apply. So this will shows you the forces experiences by the CGAP elements. And if you check for the compressive load case, it will be 0 as because it's deforming. And similarly for the CID option as a user, so in this case elemental force is 0 in the tensile load case, and for this compressive force we have some values. So we have 294.16 Newton. Thank you very much for watching the video.